This is the second video on polynomials, factors and roots. The previous video gave some insight into what we mean by the root of a polynomial, and you remember we did some plots and showed that a root is given as any value of x such that f of x equals 0. This video is going to focus on factors and show how these are related to the roots. However, we should emphasize that we're not going to give formal definitions for factors, but rather a working definition so that students understand the core concepts, because that's often what's more important. So first of all, let's give some form of general definition for a factor. Let's assume you've got some function, and this function can be made up by multiplying lots of other functions together. So we can see we've put that there. If you can create a function by multiplying together lots of smaller functions, these smaller functions are considered factors. Now, this might not be clear, so here are some examples, and then it will become a lot clearer. So here you can see we've got h of w equals e to the minus w times sine 2w. The key thing is that we've got two smaller functions multiplied together. So each of these functions are factors of h of w. So here we are, we've got a factor e to the minus w and a factor sine 2w. And if you want to see how this works out, you can see we can write h of w equals f1 times f2. That's why they're factors. In this case, the two factors multiplied together give the whole function. Now, let's look at a second example. We've got at the top here f of x equals x squared e to the minus 2x cos x minus 3. So I could write f of x equals f1, f2, f3. So that's as the product of three smaller functions, where f1 equals x squared, f2 equals e to the minus 2x, and f3 equals cos of x minus 3. So there are three factors in f of x, and these factors are f1, f2 and f3. Now look at the example lower down. G of p equals p times p minus 3 times cos p divided by tan p. Now in this particular case there are three obvious factors, but I'm going to write this again. G of p equals, what should we call it? We can call it f1 again, f2, f3 over tan p. Now I'm not going to discuss the denominator term because that's a complication we can do without, but you'll see the numerator can be written as the product of three factors. We've got a factor f1 equals p, a factor f2 equals p minus 3, and a factor f3 equals cos p. So I hope by now the students got the point. If you can construct a function as a product of different other functions, those other functions are factors. Now what about polynomials? Well, polynomial factors take a very particular form, and so the remainder of this video is going to focus on what those might be. So here's a simple example to get you started. We've got h of w equals w minus 1 times w minus 2, or if I expand this out, it's w squared minus 3w plus 2. Clearly, the left-hand side is in factorised form, because I could have written h of w equals f1 f2, where f1 is w minus 1 and f2 is w minus 2. Now, some harder examples. Where might the factors be for the following polynomials? So I've got h of w equals w times w plus 1 times w squared plus 2. And hopefully it's obvious. I can write h equals f1, f2, f3. So three factors, where f1 equals w, f2 equals w plus 1, and f3 equals w squared plus 2. And what about this example lower down? F of x equals 2x squared plus 3x plus 20 times x minus 4 times x plus 1. And again, you can see I can write this as f equals f1, f2, f3, where f1 equals 2x squared plus 3x plus 20, f2 equals x minus 4, and f3 equals x plus 1. So there we go. We can see how to factorise polynomials in a very simple form. But there's one more subtlety that we need to cover in this particular video. So here we are. In general, a system may have numerous factors. Could have a factor f1, f2, f3, all the way up to fn. Now in this case there are many possible factorisations, because not only is f1 a factor and f2 a factor, but also f1 times f2 is a factor, as is f1 times f3 times fn, and many others. So if we look at the example here, I've got f of x equals 2x squared plus 3x plus 20 times x minus 4 times x plus 1, as on the previous slide. I could factorise this as follows. So you'll notice I've got a left-hand factor, which is a cubic, f1, f2, and a right-hand factor, f3, which is monic, just x plus 1. So there we go. I've written this in terms of two factors. One's f1, f2, and the other is f3. Alternatively, I could have done a factor f1 and another factor f2 times f3. So again, I've written in the function f of x as the product of two factors. However, what you noticed on the previous slide is that some of these factors can be reduced further still, so I could write it as f1, f2, f3, and therefore write this as the product of three factors. So the key point is, a factor does not have to be in minimal form. f1, f2 is a valid factor, even though this can be reduced to smaller factors, f1 and f2. Now, if you're dealing with polynomials, it is normal, it's not mandatory, but it's normal to reduce factors to the smallest or simplest forms possible. It's not always necessary, but generally, certainly in topics like control, where you're going to be doing inverse Laplace, it's far easier if you get the factors into the simplest forms. So what are these simplest forms? Well, if the roots are real, the simplest forms take the form x plus a, or possibly x minus a. If there are complex roots, the simplest forms are quadratic, so they take the form x squared plus ax plus b. If you have a polynomial which is a cubic, you can always reduce it to an x plus a times a quadratic form.